So here's section 7.1, and in this one we're at least starting with definition 7.11 and theorem 7.11. And so our definition of an orthogonal matrix, okay, so an orthogonal matrix is an n by n real matrix, so real valued matrix, P, such that its transpose is its inverse. So P transpose P is equal to the identity. Now, they say it follows, so really this is a theorem. This is an unnumbered theorem for them. But they point out that this means the determinant of P is either plus or minus 1. And we can get that. They give the proof. It's pretty simple because we have the determinant of P transpose P is equal to the determinant of P transpose times the determinant of P, which then the determinant of P transpose is just the determinant of P. So this is determinant of P. And so this is the determinant of P, quantity squared. But we also know since P transpose P is I, we know that the determinant is 1. And so we have that the determinant of P squared is equal to 1. So the determinant of P, it had to be plus or minus 1. Okay, so that's an orthogonal matrix. So we've been exposed to this idea already. I've mentioned it a couple times. We had it on the exam. These are important matrices. Now they also mention it's P is proper if the determinant of P is positive 1. I've never seen that before. That's a new one on me. But okay, so then they look at 2 by 2 in particular, and so that's their theorem. 7.1.1, if P is 2 by 2 orthogonal, then with, I gotta toss that in. It's kind of important to mention the determinant's 1 here, so it's proper. So with determinant of P equal 1, then we can write P as cosine theta sine theta minus sine theta cosine theta. Okay, now this is really, for some theta. Now, I haven't looked at the problems yet, so I don't know. They don't prove this right here. Now, this is an interesting thing because, certainly I could take P times P transpose or P transpose times P and work with this and show it's the identity. But that's not what this theorem says. It's actually the other direction. Is it says, hey, if I know P is orthogonal with determinant 1, then this has to be true. Now, I haven't really thought about the proof for this. So what we're told that P transpose P is equal to I, and then further, the determinant is 1. Now, that'll have to do with the sign of things, I think. And so now I know it's 2 by 2. And so given it's 2 by 2, I guess I could say P is A, B, C, D. Now, I do know it's real valued, so I don't have to worry about complex numbers. But then P transpose is A, C, and BD. And so I think to get this proof, we need to take P transpose times P, which is equal to, well, I'll get A, now notice it's P transpose, so this one first, then the other. So I get A squared plus C squared here. And then I get AC times BD, or dotted with BD. Actually, theoretically, we don't know the dot product yet until later in this chapter, but so this is AB plus CD. Then bottom row, BD, and so I get AB plus CD. And then finally, we have B squared plus D squared. Now, so what I know is that A squared plus C squared has to equal 1. And B squared plus D squared has to equal 1. And AB plus CD has to equal 0. And so as I look at this, it definitely looks like that I would need something like a sine squared and a cosine squared. So it seems like we just want to look at the algebra now. So I'm just trying to think as I look at it. Well, so yeah, so I guess if I think of the A plus C, I know that, just in coordinates like that, here's A, here's C. I'm on a circle of radius 1. And so I can parameterize that. So I guess that's how we know that we get this cosine and sine thing, right? So I could parameterize this as A equals cosine theta and C equals sine theta. Okay, so and now really I would have to do a plus or a minus because I'm not sure on those. Now the point is, though, too, is that, well, I could have drawn these the other way. So I could have said this was the C-axis, that was the A-axis, in which case I would have an A is a plus or minus sine and a C is a plus or minus cosine. And that's where we're going to, and we'll check this, oh, let me stop this for a moment. Okay, I'm back. Had to get some windows measured. So we have that, both of these, the a squared plus c squared and the b squared plus d squared, we can, given that those are circles of radius 1, we can parameterize them this way. So that's where we get the sine theta and cosine theta stuff. And then we need the AB plus CD to be 0. So notice then that if say we choose A to be cosine theta, then B would have to be either a plus or minus sine theta, and then C and D. So you can, I'm not going to go through all these combinations, but I could try, oh, well, wait a minute. No, sorry. If A is, I got mixed up with the B and the C. If A is cosine, then C would have to be sine theta. Then I could mix and match the B's and D's in that I might go sine theta here and cosine theta there, which I am going to do. I could do that, or I could have done B as the cosine and D as the sine. But now then C times D has to be the negative of A times B. And so that's where we could try some different things. And so, for instance, we can put the negative here on the B. Okay, so if we do that, then we do in fact get the ones here and the zeros on the diagonal from that. So at this point, we have the A and B so we've got cosine theta here, whoops, minus sine theta there, that was the B, sine theta here, and cosine theta there. Okay, and again, we did have a little flexibility. I could have swapped the sines and the cosines, made the diagonal sines and the off diagonal cosines. But now there's also the bit of the determinant. So remember with the determinant, if this is my, P, determinant of P is, in this case, cosine squared theta and plus sine squared theta. And so I do indeed get 1, which is what we wanted. So that works. Now notice, though, all of this still would have worked if I, instead of having the minus sign there, if I put it there. And also notice that, and so I'll put that back to a plus. Notice, though, that that's P transpose, is that, if I have P transpose, then that's cosine theta minus sine theta, sine theta, cosine theta. And so there really is, which one do you call P, which one do you call P transpose? Then that's, it's actually up to us, which we choose, and the, as they show, what we go with is putting the minus sign up here. Okay, and so that's our P, and we see you know, this wasn't really a full-blown proof, but it certainly gives us the idea. You know, it comes down to these requirements. So I have those requirements plus that the determinant is 1. So with these requirements, that's where I get this parameterization of cosine and sine. And so that's why I know that if I'm going to do this, I'm going to say has to be. Now, I don't have to say it's cosine and sine of theta. I could just give them as numbers with, you know, a squared plus c squared has to be 1 and so forth. But in line with the theorem, this is, you know, this is the way we'll do it, that parameterization. So they do need to be cosines and sines, so we have that part. And we do know that we need either these two are cosines and those two are sines. Now, what happens if we did it the other way around? So, or, you know, what if we have some matrix that's, say, sine theta, a sine theta here, cosine theta, and a cosine theta, and we make one of those a minus. As we look at that, notice, let's look at the determinant here. So again, you know, this will work because it just had the diagonals either had to be the same, or it would not work. And I guess we didn't really look at that. But notice I could do it this way because the determinant of this matrix is sine squared theta plus cosine squared theta, which is 1. So we've got the proper determinant. If I looked at a plus b squared, or no, sorry, a plus c squared, or a squared plus c squared, that's those two, I would get 1 there. These two squared, I get 1. Again, I would get the 0 when I did the cross terms. So everything works wonderfully there. Now, notice though, if I did something like cosine theta, sine theta, sine theta, then all of a sudden, remember that I need these two terms oops, yeah, okay, so we're fine there. So let me erase that. So I believe that, you know, remember we got A, C, B, and D. So here we still have a squared plus c squared equals 1. We still have b squared plus d squared equals 1. And what was it? AB and, where is it back here? A, B, and C, D. So if we take AB, see, so here's our problem here, is if I take AB plus CD, that's not going to be 0 no matter what I do with negatives and so forth. So you see that's a problem if I try to do a matrix like this. So that one's not going to work. And so we're pretty much, you know, that tells us that, you know, we either have the matrix they gave us or we have its transpose, you know, one of those two things. And then, you know, we do have this possibility, but that's just not the answer. So, and remember, now they said, so it can be written this way. Well, and you say, well, oh, well, it doesn't have to be written that way. Well, okay. Remember that, let's see, well, can I remember that sine theta is equal to cosine of what, pi over 2 minus theta. And cosine theta is equal to sine of, is that also pi over 2 minus theta, I think? And so if we go with these, you see I could just make a substitution for that angle. So even if you said, oh, well, see, this is different because it's not what they say in the theorem, well, I can make it that way. So even if I decided to go with sine there, cosine there, cosine there, I can substitute pi over 2 minus theta to get my sines and cosines the way I want them. Okay. So that is whatever we had there. What were the names of those? Theorems, definition 7.11 and theorem 7.11. And so we will, I think, stop there. You're probably hoping I'll stop. And yeah, I think I'll stop there.